We can start, I think, whenever. Yeah.
I think, yeah. Partha?
Yes, let us start.
Let me start.
Very good.
Good afternoon to everyone. So it is my pleasure to introduce you today's speaker, Professor Andy Horn from University of Kent, Canterbury, UK, who is well known in the area of integrable systems. When I inquired him about the possibility to deliver a lecture in this forum, he immediately gave his consent and wrote to me that if students are interested, he will be ready to deliver even additional lectures on this topic. So I request the students to register their interest in the chat box during the talk, whether to have more seminars in this topic or not, and which month we can have this. So I understand that Professor Horn had delivered a series of lectures on this topic for the students in Italy, China, and few other countries in the lockdown period. For the benefit of MSc students, I read out his biodata in a brief manner. Professor Horn did his honors degree in mathematics in the University of Oxford and carried out his doctoral thesis in the University of Edinburgh, UK. He continued his postdoctoral work in Italy in the famous institution which people call Roma III for an year, and spent another year in the University of Adelaide, Australia. He joined in with the family of University of Kent, Canterbury about 20 years ago, and right now he is one of the senior most professors in the Department of Mathematics, University of Kent, Canterbury. Professor Horn is working on nonlinear differential and also indifference equations, cluster algebra, and number theory, to name a few topics. Besides teaching and research, he is also actively engaged in the outreach activities with the local schools and the general public. Please visit his homepage if you want to learn more about him. With this short introduction, now I invite Professor Horn to deliver his lecture. Over to you, Professor.
Thank you very much, Senthil, and thank you for inviting me. It's a pleasure to give a talk in your seminar series. I would just say, well, and thank you for the introduction as well. That was very nice. Yeah, I would just say one of the things about this pandemic, I mean, obviously it's made travel inconvenient, but I think we've realized actually that we can make the world a lot smaller, and that sometimes it's not necessary to travel. So I mean, sometimes we've been traveling around to conferences and just spending a few days in one place and then rushing off again. And actually, all that activity sometimes is wasting a lot of time, and we can actually contact each other directly online and have some very effective interactions. So obviously, it's nice to see people face to face. So I haven't seen Senthil face to face for many years, but he came to visit me in Canterbury some years ago. So it's nice to see him anyway online. Okay, so I'll start my talk. I'm going to go quite slowly. I'm going to write on the screen. So first of all, I should share my screen, and then let's see if I can make this work. So you have to tell me if you can see. Can you see my screen now? Hopefully. Okay, so I'm just gonna write.
Not at.
Can you? Sorry.
We are not.
Can you see?
No.
You're not seeing. You're not
No.
seeing. No, because it's. I pressed present. Oh
Yeah.
no! Wait a sec. I think I need to select something. Hold on. Now, can you see my screen?
No.
Still not. Wait, it's okay. It's slow. It's slow.
Yeah.
Now can you see? See?
Yeah. Now it's coming.
Yeah. Okay. So now you should see a Word file with some writing. Is that right?
Yes.
Yeah, yeah.
Okay. Good. Okay. So now we can start. Right. Okay. So as Senthil said, this is a topic. I've given lectures about this. Actually, not really much in the lockdown, but a few years before. I've given lectures, in various places. So Rome, where I was a postdoc, and Beijing, and well, Sydney, and anyway, a few places, as well as to my students in Canterbury. So, and it's a topic that I keep coming back to, which I've been interested in for many years. In fact, it's a topic which my PhD supervisor made me learn about this topic when it first appeared in the literature. And he was quite clever to make me. He made me. I mean, I think he didn't read the paper of Camassa and Holm carefully, but he told me to read it carefully and explain it to him. And this was a very good exercise for a student, because I did all these calculations and then I really understood what was in the paper. And then I ended up working on it myself, first of all, when I was in Rome. And then shortly afterwards, I was in the Newton Institute in Cambridge for a meeting, and I was organizing a summer school in a long program. And de Gasperis was giving, I invited him to give lectures in the summer school. And he gave a lecture about a new equation, which was like Camassa Holm. Well, he gave some lectures about his method of asymptotic integrability, which is an integrability test. And he produced a new equation, but he didn't know anything about it. I mean, he just discovered it with his PhD student, Michela Procesi. But then I sort of recognized that it was very similar to Camassa Holm equation. And then I started working on it. And then Darrell Holm showed up in Cambridge at the same time. And so actually then me, Tony, and Darrell, we all worked together on this new equation. And it was a very kind of exciting and fruitful interaction. And we did quite a lot of stuff together. And then I've kept on, working on this on and off on this problem. Then with my colleague Jinping Wang in Kent also, and various other people. So anyway, I just want to give you a broad introduction to this topic, but I could give more detailed lectures in the future. As I said, if you're interested in it, I'm happy to give more lectures, because I've got lots of lecture notes that I can talk about. Okay, but let's say the problem is, if we start off with the KdV equation. Let's start off with, so I'm going to write now. So the KdV equation for the vector Vries, which appears in shallow water wave theory. And how does that look? Well, it's an evolution equation. So you have the time derivative of u, which is in shallow water theory, u is the height of the fluid above the surface of the water, the height of the fluid from the baseline, if you like, in a channel. And then in KdV theory, okay, well, you have some linear dispersion. So I'm using subscripts to denote partial derivatives. So ut means the partial derivative du by dt, and uxxx means the third partial derivative with respect to x, which is in the fluid context is the distance along the canal. So that's the linear part. And then, okay, then you have some non-linearity. So you have an advection term, which looks like this. And okay, you can put some coefficients as well. You also normally have, say, with another coefficient, you would also have some another dispersion term, and there would be some constants as well, some physical constants. So what I'm going to do for now is I'm just going to put some oh, wait a sec, I want to change my color of my pen. Let's see if I can get a red pen for a change. Okay, so in front of all these terms, I'm just going to put a dot, and that means there's going to be some coefficient which, in the fluid context, would depend on things like the height of the undisturbed water surface and the acceleration due to gravity. And so okay, there are some constants, but actually in KdV we can scale these constants to be whatever we like. And then we also often do a Galilean transformation. So we go to a moving frame and we can remove the UX term. Okay, but that's what the terms of the KdV equation are in a sort of physical context. Okay, now, so what's the story with Camassa and Holm? Well, I mean, if you ever studied KdV, I mean, the physical derivation, and I'm not an expert in this area, but in the physical aspects of it. But if you study the KdV equation, then it's an asymptotic derivation. You're looking at long waves on shallow water, so small amplitude waves on shallow water, let's go now to what did Camassa and Holm do. Well, they looked at this asymptotic theory of water waves, of shallow water, and they said, well, how about if we keep some terms at higher order in the asymptotic series? So okay, so the simplest thing would be you just have a linear equation, and then you have some nonlinearity. But then if you do your asymptotic expansion, then you'll have some higher nonlinear terms that appear. So what Camassa and Holm did is they added on some higher terms in the asymptotic expansion. They included some higher terms, and they claimed that this would give some, if you like, some higher corrections to KdV theory. So what are the terms that they added on? Well, first of all, they added on. So let's sort of forget about KdV for a moment, so we can rub that out. And then what they wrote down is, and let me actually go back to the black color. I think it's maybe easier to read. Let's just see. So I'm going to rub out the red, and I'll go back to writing black again. Okay. So what the equation that they got. Okay, I'm going to leave a space. They had some higher corrections. So they had a UUX term, and as I said, well, like in KdV, you have a freedom to, you have these coefficients that will appear, but actually in KdV theory, you can scale all these coefficients to be anything that you like. But I'm going to put some, now for Camassa Holm, I'm going to put some particular coefficient, which is going to be 3. Okay, and then I'm going to put some of the correction terms on the right hand side. So the correction terms that they had were 2ux, uxx, and then uxx, xxx. So these are some quadratic nonlinearities, the higher order with higher order derivatives. And okay, also they had, now I'll go back to the red color again, just to write them in. They also had some the same kind of linear dispersion as KdV, because those terms also appear. So the other one, I'm going to write it just underneath. And also now I'm going to put a dot, a colored dot in front. Okay, so there's some coefficients there in front of the linear dispersion terms, but I don't really care what they are. Now, okay, if you're looking at this as you want this to be a fluid model, then it's quite important to have that linear dispersion there for various reasons. But if we're just interested in this equation, oh, and I'm sorry, and I've missed out the most important. I'm missing a term, which is the most important term.
XXT.
Yeah, exactly. Thank you, Partha. I think that was Partha correcting me. So there's another term here, yeah, which another linear term, which is quite important. Well, very important, in fact. So the terms that are added, if you like, let me underline them. So this term, these terms on the right, and this XXT. Okay, so these are the correction terms that Camassa and Holm found from higher order asymptotic corrections. But now, if we're just interested in this as a mathematical model, then some of these terms we can get rid of. And because there's an XXT term, well, if we do a Galilean transformation, so, and also a shift. So what do I mean? Well, let me be precise about that. So Galilean transformation means that we go to a moving frame, moving with velocity v, let's say. T is going to stay the same. And then the shift, we actually shift the field u by some constant. So we actually change the background. Okay. Now, if you allow these transformations, so a moving frame, but also shifting the background of the equation, then we can completely remove the dispersion terms that were there. So we can remove both of these terms, okay? So I'm going to forget about those terms for the rest of my talk. But obviously, if you're interested in a physical model, this is very important because you care about the speed of the waves, and also you care about the background, the boundary conditions. And this transformation changes the boundary conditions. Okay, but if we do these transformations, then what we end up with is, now let's write it in a, let's write it again. There we are. So that's what we're left with. This is the Camassa Holm equation in, I would say, non-dispersive or dispersionless form. So we've removed all the linear dispersion. And if we, you know, from a mathematical point of view, essentially all the, let's say, algebraic properties of the equation to do with its symmetries and integrability, which I'm going to discuss, it's sufficient to work with the dispersionless version of the equation. If you're only interested in, let's say, sort of the mathematical properties or the algebraic properties and the symmetries and so forth, or integrability, then this is the sort of simplest form of the equation that you can work with. It's also rather instructive to rewrite it when you have it in this form. So I'm going to write this in red. To write it, so it's clearly not an evolution equation for U, at least not an evolutionary PDE for U, because of this UXXT term. Okay, but if we introduce an inverse Helmholtz operator, we could write it as UT equals something, and that would have some derivatives and also some integral term, which would be the Helmholtz operator, which the inverse of it would be an integral operator. I'll discuss that more detail in a minute. But we can also write it in a nice form like this, a very neat form. If we introduce a new variable, I call it M, which is like a momentum density, and then we can write this form of the equation. Where this momentum density is this Helmholtz operator in one dimension acting on U. Okay. Now, as I said, I'm not an expert in the physical derivation of shallow water theory, but it's more or less understood that the original derivation of the Camassa Holm equation in the paper of Camassa and Holm from 1993 in Physics Review Letters, and then they wrote a longer paper with Hyman, where they went into a lot more detail. The original physical derivation has some problems. So when they were balancing different, there are two sort of asymptotic parameters. And, you have to look at whether a parameter is small or large, and some of the balances that they did had some small terms and large terms appearing in the same place. So the original physical derivation of the equation, which has dispersion, is definitely problematic. But subsequently, they, Dullin, Gottwald, and Holm did a more careful analysis. And they also found a one-parameter family of equations, which I'll tell you about shortly. And then actually, Konstantin and Lanis also have a very long paper in Archive of Rational Mechanics, where they actually derive this Camassa Holm equation and also this other one-parameter family of equations called the B family, which I'll tell you about. Actually, in their paper, so U, the velocity field, if you like, it's not. I mean, U is like a velocity field, but in Euler's equations or Navier-Stokes equations. But actually, and in the shallow water theory, U is the height of the water. So it tells you where the water surface is. But in the Konstantin and Lanis derivation, actually, U is actually the horizontal component of the fluid velocity at some fixed depth in the fluid. And they have a one-parameter family of equations like Camassa Holm, which, the parameter tells you which depth you're measuring the fluid velocity at. And then if you know this horizontal component at any fixed depth in the fluid, then in fact you can reconstruct the water surface. You can recover it by some other operations, if you like, integrations and things. So anyway, in that context, U does not represent, you know, height of the water surface as in the usual KDV theory. But anyway, I'm not going to say really more about the physical motivation or derivation, except that there are a number of equations like this which appear in, you know, physical context. There's also an equation in theory of elastic rods, which is very similar. And okay, if we care about what we're modeling, then it's important to have the linear dispersion, because actually the solutions of the equation will be smooth waves. Okay, if in that case, when you have some background, when you have some dispersion. But if we don't care about exactly about that, and we just work with this dispersionist form, then actually it's where you see probably the most remarkable thing that Camassa and Holm observed, which I'll tell you about, which is called the Picon Solutions, which are some peaked soliton solutions. Okay. But they also proved that the Camassa Holm equation is an integrable equation. They constructed a lax pair for it, and a bi-Hamiltonian structure. Now, in fact, the integrability of the Camassa Holm equation was already somehow understood much earlier in the literature. So in the work of Focas and Fuchsteiner on what they called hereditary symmetries, or the theory of recursion operators, they found they found some equation which should have been Camassa Holm, but at least in more than one of their papers, they actually wrote the coefficients wrong. So I said, you know, when they have these physical constants, we scale them to be whatever we like, or we scale them away. But these numbers that appear in the Camassa Holm, so in the form that I've got it here, the 3 and the 2 and the 1 here, these numbers are really fixed. I mean, I can obviously rescale U, but you know, once I fix the scale, then these numbers are fixed, and it's quite important. If you look on the left, you have 3, and on the right you have 2 and 1, and 3 equals 2 plus 1. That's quite an important equation, as you'll see in a minute. So these numbers are really, you know, fix the equation. If we change these numbers, then we will change the properties of the equation, destroy integrability, and so forth. Okay. But let me talk about, you know, what did Camassa and Holm discover. So wait a sec, I just need to yeah. So I need a new page. For some reason, Word likes to put the pages in the wrong order. Okay, so just bear this equation in mind, and I'll mostly work with this form, this momentum density m. So let me say a bit more about that. So if we work with this, m is somehow a natural thing, and it's like an evolution equation. So m is u minus uxx, and we can also think of the inverse of that, that u is given by a convolution of m with an integral operator, so the inverse of the Helmholtz operator. And G is a convolution kernel, which is the Green's function for the Helmholtz operator. Okay. So what's the properties of this Greens function? Well, the defining property is that if we apply the operator, we get the delta function. Okay. Now, so the Camassa Holm equation, it has a and like the KdV, the Lax equation, the Lax operator is the Schroding operator. Here, it's a little bit different. It's instead of a Schrodinger equation, we have a kind of acoustic equation. So in the Schrodinger equation, the potential for KdV appears, and then there's the eigenvalue for like the spectral parameter lambda. But here in this equation, you see the field M in this acoustic spectral problem. The field M is multiplying the spectral parameter, which is a little bit different. So it has a Lax pair. Then it has what's called a bi-Hamiltonian structure. So the bi-Hamiltonian structure, you can write it as a Hamiltonian equation in two different ways. So if we write the equation for M, we can write it as, let's say, B1 dH1 by dm. So that's Hamilton's equation for M. And then we can also write it as a different Hamilton equation with a different operator B2 and a different Hamiltonian. So what are these operators? Well, one of them is local. So if we take we can take this operator okay, and then we can take the Hamiltonian to be well, there are different ways we could write it, but it's basically a proportionality. It's the H1 norm of U, but we could also write that as a half of, you do integration by parts, you could write that as U times M dx. And we could also think of this, another nice way to write it is if you think of this as an L2 pairing between M and U, and then you see that it's, if you think of M is like a momentum variable and G is like a metric, or actually a cometric, then this is, so again I should put a half in front. This is really like a geodesic Hamiltonian. In fact, this is a, if you know about Arnold's interpretation of Euler equations as a Euler-Poincare equation as a geodesic equation on the diffeomorphism group. Well, again, the Camassa Holm equation. So the KdV equation has this interpretation with the L2 metric, and the Camassa Holm equation has the same interpretation with the H1 norm, H1 metric. So you can think of it as a geodesic flow on a diffeomorphism group with this metric. So that's one Hamiltonian structure. Hopefully, I may have. Yes.
Andy,
Yes.
actually, you can also reinterpret it as a H1 norm with respect to U, if you take into account.
Sorry, yeah, no, it's the H1 norm of U here. Yeah. This
H1 norm.
What I've written at the top. This
Is actually H1. H1 is a well.
This here is the H1 norm of U up to
exactly.
Yeah. So that's the H1 norm. Yeah, half of the H1 norm of U, half of the square of the H1 norm of U. Yeah. Okay. So that's the metric that you're using. But then, if you like, writing in terms of M is the, if you think of Legendre transformation, M is the momentum. So G is like the cometric. Okay, so that's so it's the U is like the sort of Lagrangian variable, and M is like the Hamiltonian variable if you do Legendre transformation. Okay, so but then the other operator is so hopefully I got this the right way.
That's right.
Wait, I got them hold on, I got them the wrong way around. Let me, so this B1 is not right. Hold on. Let me get to the eraser. Sorry, I should have written the variational derivative of this is U, right?
Yes.
If you calculate it. So this operator should be what I just wrote below. Hold on. Let me do that, correct that. So the operator should be minus M dx plus dx M. So this is a skew symmetric operator which satisfies the Jacobi identity. So it gives a Hamiltonian structure. It gives you a Poisson bracket, and you can think of this. This is actually a Lie Poisson bracket as well, that's defined by the operator. Okay, then the other operator is the one that I just rubbed out, B2. So let me write that correctly. So B2 is this one, is dx is just constant coefficient. So this is clearly skew symmetric and satisfies the Jacobi identity, whereas the other operator is a little bit more complicated if you want to check the Jacobi identity. But now the Hamiltonian is a bit more complicated for this one. So it's a half of UX squared plus U cubed dx. And okay, there may be some minus signs. You have to check. That's a good exercise for the students to check that I didn't miss a minus sign anywhere. But anyway, I think the first equation now is correct. B1 and H1 is definitely correct. And there you have to do a calculation to check B2. So okay, so bi-Hamiltonian structure is sort of what we associate with integrability. And the reason is that this allows you to define what's called a recursion operator, and that allows you to generate infinitely many symmetries of the equation, starting from trivial symmetry. So if you start from, so the recursion operator is, well, let me see. So if we want to do, if we start from mx, yeah, so we want to do B1, B2 inverse, right? So if you start from a trivial for so the trivial symmetry is just the flow mx, the translational flow. So if we apply this recursion operator to mx, then okay, we get the inverse of the Helmholtz operator. So again, we may want to put a minus sign in front. Let me see. 1 minus x squared dx. No, yeah, we got the minus sign in B1, so that's okay. So now if you work out this equation, you'll find that this is, so mx, if we take, if you like, dm by dt is mx, that's a trivial linear equation. But now we apply this recursion operator, we get the Camassa Holm equation. Okay, and then if you apply powers of r successively to mx, you get infinitely many symmetries of the Camassa Holm equation. But now actually, if you want to get local symmetries, you should actually apply the negative powers. You should apply r minus 1 and then r minus 2 and so on. And then you'll get equations that just depend on m and its derivatives. And those equations are basically what's called the Harry-Dim hierarchy, which is related to KdV. So if you take inverse powers of R, this operator, you'll get infinitely many symmetries of the Camassa Holm equation. And then this theory that I mentioned of Forecast and Fuchs-Steiner, and then also Gelfand and Dorfman, this guarantees that all of these flows commute with each other. And that's what we mean by integrability, that we have this infinite number of commuting flows. And you can also derive these flows starting from this last equation, which I just wrote above. If you now look at the different possible time evolutions for the wave function psi, then you'll find that you can generate these infinitely many commuting evolution equations in M. Okay, so that's integrability. But as I said, somehow this aspect of integrability was already understood. Apart from, Forecast and Fuchs-Steiner didn't write down the equation originally with the right coefficients, so they didn't really, they missed something there. Fuchs-Steiner has an article where he says, this was sort of a missed opportunity. But in a way, this is not the most remarkable thing about the equation. The really remarkable thing, so now if I go to a new page, is what's called the Picon Solutions. Okay. So the really amazing thing is that you can find infinitely many, an arbitrary number of solitons, an arbitrary superposition of solitons. But if you've ever studied the KdV equation, then you'll know that the superposition of solitons in the KdV equation is a nonlinear superposition. So if you write a single soliton which has the shape of Czech squared, the hyperbolic secant squared, and then you try to calculate the 2 soliton solution or the 3 soliton and so on using inverse scattering or using Hirota's method, then the formulae for the solitons become rather complicated. I mean, they're very nonlinear expressions that describe how these waves interact. But what's amazing in the Camassa Holm equation is that you can take an arbitrary number of solitons, and if you look at this formula for U, Well, each of the solitons, now the shape is not a hyperbolic secant. The shape is this Green's function, e to the minus mod x. So this is the sort of shape with a, but has a discontinuous derivative at the peak, at qj, for j equals 1 to n. So each of those positions, and there's functions of time. But otherwise, this is really a linear superposition, right? It's just a single picon would just be a constant c, the speed, times e to the minus mod x minus ct. And this looks just like a linear superposition. You've just added them up. So how can this work in a nonlinear equation? Well, these are what are called weak solutions. So you have to do some careful analysis, and you can see that m here is given by sum of delta functions. So you have to do some careful. How can we get this to be a solution? Well, you need to look what happens at the peak positions, and because it's a weak solution, you need to integrate against test functions which have support at the peaks, at the positions qj. And if you integrate with two different types of test function at each position, for this to be a solution, you need to have ODEs for the PJ and the QJ. So what are the ODEs? Well, they're exactly Hamilton's equations in finite dimensions. So Hamiltonian system with n degrees of freedom, and this is a geodesic type of Hamiltonian. So okay, so if you know about the Hamiltonian formulation of geodesic equations, this would be in Hamiltonian form. Then this term here is the cometric. So this is like the Hamiltonian H1 that I wrote above. And in fact, if you take this Picon, so let me just make this a bit smaller so you can, hopefully you can still, oh, now you can see two things. Hopefully you can still read okay. So if you look at this Hamiltonian here, H1, or actually in this form, if you substitute the form of m with the delta function into this L2 pairing, then you'll get exactly this Hamiltonian capital H in finite dimensions. So you restrict this Hamiltonian H1 to finite dimensions, to the Picon submanifold, and you get the Hamiltonian for the dynamics of the peak positions and the amplitudes, which is qj, and the amplitudes, which is pj. And this is a completely integrable system as well in finite dimensions. So this is quite a remarkable, this is really a remarkable thing. I mean, so this is an integrable system. In the sense of the Liouville theorem, with n degrees of freedom. This, I would say, is the most amazing thing that Camassa Holm discovered. Now, can I just check? I'm supposed to talk for another half an hour. Is that right? Is that okay?
Yes.
Yeah,
Yes.
I mean, I probably won't. So the problem is I can talk the back legs off a donkey, as they say. I can keep on talking forever, but I don't want to talk for another half an hour because I want to give you time to ask me some questions. But I am going to say a few more things before I stop talking, okay? So I just want to sort of let you know where I'm going. But if you have any questions now, please ask. Does anybody have any questions so far that they would like to ask? Or?
I don't. Partha, do you have some doubts?
I have question, but it's I will encourage students to interact with him first.
Okay, thanks, Pata. Well, Pata's already made a good contribution to start. Okay, let me carry on a bit more. So yeah, so I think really this is the amazing thing about this equation, or what we call Picon equations in general, is that you have these weak solutions which are given by really a linear superposition, and you have to do some careful analysis to verify that this is a solution. And I'm very grateful that my supervisor kind of forced me to do this calculations when I was a PhD student, because it allowed me to, work on this problem, years later. But this was really a new phenomenon in integrable systems. This hadn't been seen before. Of course, if we're interested in dispersion, then these solutions are not physical solutions. Okay, they have discontinuous derivatives, but you can see them as being a limit of smooth solitons. So if you do this Galilean transformation and shift the background, then the equation with dispersion has smooth solitons, which look very much like KdV solitons. And you can do the standard, well, it's a bit more complicated, but you can do inverse scattering, and you can derive these solitons. And then somehow, if you now vary the background, the parameter, if you sort of have the dispersion terms, you can let the background go to, you can think of the equation without dispersion on a non-zero background, which has smooth solitons, and then you let the background tend to zero, and in that limit you get the picons. Or you can think of having the equation with linear dispersion, and then you let the dispersion go to zero, and then again in that limit, it's an equivalent limit, you get these weak solutions, the picons. Okay, so this is really an amazing thing that Camassa and Holm discovered. Okay, so what I want to say for the rest of the talk is, how does it generalize to other equations? Well, the first thing is, as I already mentioned, there was this equation of De Gasperis and Procesi. Okay, so let me get a new page now. And I'm going to so as you see, Word orders the things in a strange way, but so other equations. So I'm not going to write out the whole names, but De Gasperis and Procesi, their equation, you could write it like this. So I said before that 3 equals 2 plus 1 is very important. And here it's not 3 equals 2 plus 1, but 4 equals 3 plus 1. Okay, so there's the 4 in the advection term on the left, and then 3 and a 1. Again, we can write it in this way.
It's a special case of Holm-style equation, B-field equation.
Yes, I'm going to say that in a minute, Partha. Hold on. Actually, I don't like this name, Holm-style equation, because actually we wrote down this equation in our paper before her. I mean, with Holm and de Gasperis, we already wrote down this. So I prefer to say the B family.
So next time I will do that. Sorry.
Yeah, it's well, I mean, the thing is, all of these things were going on at the same time almost, but the point is, we were in Cambridge with de Gasperis and Holm, and we just, we started discovering the amazing properties of this de Gasperis-Procesi equation, and then the natural thing was to put a parameter there, because when b equals 2, it's Camassa. So this is de Gasperis-Procesi, which is also an integrable equation, and then this family of equations with a parameter b, when b equals 2, it's Camassa and Holm, and when b equals 3, it's de Gasperis and Procesi. But the question is, to what extent can we generalize the properties of Camassa and Holm and de Gasperis-Procesi to all values of b? So when we started working with this, it was Darrell's idea to say, well, let's put in a parameter and see what we can do. And then I was very fortunate that I understood things about Lax pairs and Pauli-Levé analysis, and I was able to derive. To begin with, I was able to derive a Lax pair for de Gasperis-Procesi equation and prove the integrability. But the thing is that this B family is really a nice family of equations, and so yeah, we were looking at maybe the Hamiltonian properties of this family and other properties of solutions, and then Darrell went back to Los Alamos. At that point, he was just sort of in the process of moving to the UK, and he went to Imperial College around this time. But he went back to Los Alamos to kind of tidy up his business there, and I think there was some politics going on. I think the nonlinear science division that he'd been in for many years were annoyed that he was leaving for Imperial to take up a chair there, and they tried to deny him his pension rights, I think, and he basically switched into the computational science division just before he left, and that's when he worked with Martin Staley. So we had this new family of equations, and then he got Martin Staley to do big computations on the supercomputers in Los Alamos, doing Fourier spectral decomposition methods to integrate these equations, which is actually itself is a rather challenging problem. I'm not an expert in numerics, but the numerics of Camassa Holm equation and these kind of equations is actually very challenging. So he did very high precision. This is more than 20 years ago. He did very high precision Fourier methods, and since then other people have been working on other methods that can do numerical integration of these equations, and there are many different methods, but it's itself an interesting problem. But what are the properties? Well, it's actually a Hamilton. It's not bi-Hamiltonian, but it does have one Hamiltonian structure. For all values of b. I won't write it down. It's a little bit, but I mean, if you press me, I can write it down, but I'm not going to write it down now. But anyway, just suffice to say that there is an operator B, but it actually, this operator really corresponds, in the case B equals 2, it corresponds to the third Hamiltonian structure of Camassa Holm equation. And in the case of B equals 3, it's the second Hamiltonian structure of the de Gasperi-Spicese equation. But anyway, there is an operator B that works for capital B, which works for all little values of parameter B, okay, all values of this lowercase b. So it's Hamiltonian.
So it is not integrable because it's not bi-Hamiltonian. There is
that's right. Yeah, that's right. But it has Picon solutions.
Yes.
For all B as well. And because of the Hamiltonian structure that exists for the PDE, these are also Hamiltonian equations for the Picons, although they're Hamiltonian ODEs, although they're not canonical. So they're not in the canonical form that I wrote here. You can write them actually in exactly the same way, just insert the second equation for the momenta, or the amplitudes, multiplied by b minus 1. Okay, so when b equals 2, you indeed get the second Hamilton equation for Bj. But when b is not equal to 2, that's no longer a Hamiltonian system, but h is the same, but h is not a constant quantity for if b is not equal to 2. So this is not the Hamiltonian form of the equations, as it were, but there is a Hamiltonian form of the equations. It's just non-canonical. Okay, so there are Picon solutions. Then there are many other interesting properties like wave breaking and so on, which is another thing which is important in analysis of fluid problems. And also occurs in Camassa Holm equation. But another thing is that there's what's called a reciprocal transformation.
Right.
And the reciprocal transformation is a change of it's a change of independent variables. So you have a conservation law which I can write as PT plus UPX equals 0, where P is m to the power of 1 over B. So this is when B is not 0, okay? And now if you do this, so, okay, let me, is it gonna do some, oh, whoops, it's made it minuscule, I'm sorry. So I hope you can read okay, everything. I'm gonna put in a new page. Okay, so what is the reciprocal transformation? Just not writing transformation, but well, we can, but given this conservation law, we can write this one form. And obviously this is a closed one form which follows from the conservation law. If you work out d squared, well, it's exact, so it's closed. So d squared x equals 0, and that's equal to what is d squared x? well, that's pt t wedge dx minus upx dx wedge dt. And then if you combine that, you'll see you get that conservation law that I wrote over here, right? So the fact that this transformation is well defined, it follows from the existence of the conservation law, and then you can transform the derivatives d by d little x, because just use the chain rule, becomes p, and then dt becomes dt plus pu dx, if I didn't make a sign. Maybe my dx by dt, so minus, sorry, minus, yeah. But that's just the chain rule. Okay, and then if you do that, then you can get a new PDE for P, and no, sorry. So what you get is new PDE for P as a function of the new independent variables. And this equation, it looks like it looks like this. So this is a third order, no, sorry, there should be a P as well. This is a third order PDE for P. And when B equals 2, this is like a third order generalization of the Sine-Gordon equation. And when B equals 3, this is like a third order generalization of what's called the Siseka equation. And those are both integrable equations. And in fact, these equations are also integrable, and they have the Painlevé property. So you can so let me see, what can I say? This is sort of more or less, I'm almost going to finish, but these are the only integrable cases. Okay, so you can see that from, if you somehow, from the Painlevé property for this PDE, but also you can get it from the perturbative, well, from the what's called the perturbative symmetry approach, from requiring infinitely many symmetries, which was done by Novikov and Mikhailov. Or if you go back to where we started, which is here over on the right, De Gasperis and Procesi, they basically wrote down all possible third order PDEs with quadratic nonlinearity. And what was the result of De Gasperis and Procesi? It was that only out of all third order equations, you know, with all possible derivatives in x and t and so on, the only possible equations that are integrable are KdV, Camassa Holm equation, and then this new equation, well, which was then new, the De Gasperis-Procesi equation. Those are the only equations that they discovered by their method of asymptotic integrability. Okay, so I almost want to finish. I want to leave you some time for questions, but the last thing I want to say is about what's called the Soliton resolution conjecture. So there's a very nice article by Terry Tao, which is called "Why a Soliton Stable?" And what he talks about is a phenomenon. So it's a kind of a folk theorem. And if you have any nice dispersive wave equation, so sort of it could be KdV type or NLS type or some other type, it doesn't have to be integrable. So you can take KdV with quartic nonlinearity, for example, and that still has solitary wave solutions. And if you look at the initial value problem, then you find that it splits up into solitary waves. So you start with an initial, initial value problem, and then the initial, whatever the initial profile is, it will break up into solitary waves and radiation asymptotically as time goes to infinity. And so it's got nothing to do with integrability somehow. Photons, you could say. It's got nothing to do with integrability. It's a much more general property of dispersive nonlinear wave equations. And this is observed in this family as well, this B family. But what's interesting is that it depends on the parameter B. So let me just, let me just go to one last page. And I'll make it bigger again. So this is sort of based on the numerics that Holm and Staley did, and that other work that I and other people have done since then. If B is greater than 1, then you get picons. So you start with any initial profile, and it breaks up into, you start with some initial pulse, and then it will spew out a train of picons of decreasing size and velocity, which will move out to the right. Okay. If B is between, if B is between -1 and 0, sorry, -1 and 1. Okay, 0 is quite important as well. You get what's called ramp cliff solutions, which is basically like, so you start with your profile, and then what happens is it forms like a steep ramp, and then that drops off a cliff. And this is like the Burger's equation, if you know the Burger's equation. And the ramp is like x over t, basically. It's like this steep part is basically like a straight line. Well, it's actually x over b plus 1t. Okay, and then for b less than -1, there are some solutions called Leftons. And what are Leftons? Well, you start with your initial pulse, and then there are some waves which move out to the left, and they're exact solitary waves. You can work them out. They're given in terms of Sheck, but then they freeze. So they move to the left, they form a train of solitons, but they freeze. They're stationary solutions. Okay, so at least for B bigger than 1 in magnitude, this looks like soliton resolution, that you always get solitons plus radiation. So for B bigger than 1, you get picons plus radiation. For B less than -1, you get leftons plus radiation. So you have the stationary things which freeze, move to the left, and they freeze, and then once they've frozen, then the radiation vanishes as t goes to infinity. And then between -1 and 1, it's more like Burger's equation. You get this steep ramp cliff solution. Okay, so that's all I wanted to say, but I would just say that there's a lot of interesting analysis to do to actually prove. I mean, nobody knows how to prove soliton resolution, or, well, the question is actually how to formulate it correctly. there are results on stability for some types of equation, but people are just starting to prove results about this. But I mean, really, to formulate it, you need to talk about the space of initial data, put a measure on that space, which is very difficult, and so on. But okay, stability, people are starting to prove results now about stability of trains of solitons, and even for this B family, there are some new results quite just the last few years. La Fortune and collaborators. Okay, so anyway, that's where I want to stop, but please ask me questions. You're welcome to carry on asking me questions for longer if you want. Okay, so thank you for listening.
Yeah.
Shall I stop sharing the screen? I think.
Yes, I think.
Actually, before I do, I would. I actually wanted to share just. This is a paper. So here's a ramp. This is the initial Picon profile, and then this is a ramp for B equals 0. This is a ramp. This is time going upwards, and then at some time they switch on B equals 2, and it becomes the Camassa Holm equation, and then they get a train of Picons coming out. Okay, so that's where I wanted to stop. Okay, thank you.
Yeah, it's open for questions. The session is open for questions.
Professor.
Okay, please ask. Stalin, go ahead. Go ahead.
Hi.
Yeah, Professor, these equations, Camassa Holm and Dispersion process equations, have smooth solution also, right?
Yeah, that's right. I mentioned there are smooth solutions and there are smooth solitons. I mean, they all B family. There are some smooth solutions. There are smooth solitons, but if you take away the dispersion, then the smooth solitons are on a constant background.
Okay.
So the solitons on a 0 background are the Picons, right? If you have the dispersionless equation. Yeah.
Okay. Without the dispersion, also we can have a smooth solution, right?
Yeah, but on a constant background. Yeah.
Okay.
Or periodic solutions. Yeah.
Yeah. Okay. Thank you.
Andy.
Yeah.
Thank you for the lovely talk. Excellent. Now I have like to talk few things and like to ask you something. You see that when I worked on B field equation, it's a long time ago. I noticed that I was planning to formulate in terms of the Hamiltonian PDE, in terms of the the diffeomorphism groups and in fact of the adjoint representation thing.
Yeah.
But then I noticed that you need to invoke certain things, some other terms, which later on I wrote a paper called Metriplectic Geometry, Metriplectic Structure. Because the symplectic part as well as some kind of metric driven flow, that is a double bracket formulations by people are doing. So and in fact not only this one, this KdV-Berger equation is also play the same type of thing, KdV and Berger equation. So now
that with extra terms, you're saying?
With extra terms, in order to handle the extra terms, you have to extend your Hamiltonian program into the metriplectic programs. And in fact, it was actually a paper in Journal of Nonlinear Mechanics. Now the question is that, because that time people were all discussing about this thing, later on people now accepted that it is a metriplectic infinite dimensional structures. Now, I'd like to ask a couple of simple things. Number one is that there is a, some kind of correspondences you showed, we know that when you have a Camassa Holm equation, if you look at the finite dimensional Hamiltonian, Pi Pj e to the power minus Qi Qj mod. So this kind of correspondences are there in the B field equation? If it is there, then how can I write down that Hamiltonian equation?
So wait a sec. So one thing is just to mention that actually you can formulate the all the B family as a geodesic equation, but with respect to a non-metric connection. So there's I don't know if you know, there's a paper of Escher and Kolev quite recently about maybe 7 or 8 years ago or so. So you can if you take a non-metric connection, then you get it as a geodesic equation for any B, and then the Camassa Holm equation is just the case where your connection happens to be, metric connection. But so you're interested in how to reduce from the infinite dimension to the finite dimension? Is that what you?
Right.
I guess my approach is really just quite sort of elementary and lowbrow, but just basically you substitute the. One thing is actually you can start from a Lagrangian. You can derive this Hamiltonian structure effectively. There's a Lagrangian structure for any B. And then when you look at the level of the solutions, say the Picons, you can just substitute. You can substitute the Hamiltonian, as I said, the solution into the Hamiltonian and get the finite dimensional Hamiltonian. You can also substitute the solution into the Poisson bracket equation. This is actually we did a long time ago with in a paper with Darrell, where we computed the finite dimensional bracket from the infinite dimensional one. So you can, this works. So in Camassa Holm equation, for example, you have to do lots of calculation with distributions, but basically you can calculate the Poisson bracket. You can get the canonical Poisson bracket for the Picons, starting from this Poisson operator.
Yeah, but for the B field,
same thing for the B family. For the non-canonical bracket between the P's and the Q's, you can get it by essentially substituting the solution ansatz into the infinite dimensional Poisson bracket, and then just do lots of integrations. With test functions, you can prove that the finite dimensional variables satisfy. You can derive the bracket basically. So
has anybody done it?
We've done what?
Has anybody done it?
Yeah, I've done it. That's what I'm saying. We did it in a paper with Darrell.
That's the DHH paper. I know. Okay.
No. I think it's a paper just with Darrell in Journal of Nonlinear Mathematical Physics.
Okay. I will check it.
But also, I've done it. I've done it for some other equations. In a paper with Wong about the Novikov equation, we also derived the Poisson bracket for Novikov's equation, Picons, in this way. I don't know if we give all the details there, but also I have some paper with some students about some non-integrable equations. There's what's it called? Some other coupled Picon equations. We did the same approach to calculate the Poisson brackets for the Picons. Also for non-integrable equations. Let me see. I'm just. What was the one? Just trying to think. Popovits. That's right. There's the Popovits wrote down some coupled Picon equations, and again we could derive the reduction Picon Solutions for this equation as well, using the Hamiltonian operator for the PDE. Yeah, there are many examples. I can send you all the references.
Okay,
Yeah.
please. And Popovich is super Camassa Holm, because super Camassa Holm we worked with. I had a paper with Peter Olver about this.
No, this is a different Popovich one. So this is some coupled.
Please send me the reference. Okay.
I don't know, but I mean, I know he sometimes uses the super formulation, but to derive just the ordinary Poisson structures. But no, there's some coupled system of Popovich which is not integrable. But anyway, it's still Hamiltonian, and again we can. Yeah, it's quite interesting. There's a Hamiltonian structure in dimension 3n, and then there are some Casimirs, and it reduces down to something in canonical, sort of, well, not canonical, but something in dimension 2n. So there's yeah, you can derive the whole story, if you like, starting from the infinite dimensions.
Right. Another question, short, quick question. Basically, in KdV equation, I know that non-holonomic deformation is possible, and in fact, what is you call it a KdV6 by the Boris Cooper-Schmidt is actually in some way KdV plus source term. Now you can do it for NLSE and other places things. Now, is it possible to do for the Camassa Holm equation? Because I didn't see it, because I was trying to do a non-holonomic plus quasi-deformed integrable systems. You can look at some of my recent papers. So is it possible to do for the Camassa Holm or any B family?
I mean, in principle, I'm just thinking, I mean, what you call this non-holonomic deformation, I mean, in the KP theory, somehow they're like squared eigenfunction symmetries. Is another way to view them. So basically you end up with, you have your equation and then a source term, and then sort of coupling to a nonlinear, to a linear equation, essentially. So if you like, the source term is somehow an eigenfunction or a squared eigenfunction. So in principle, you could, well, I mean, here's an idea. If you start from the squared eigenfunction symmetry of KdV, and then you apply the reciprocal transformation, take the negative flow and then apply the reciprocal transformation, then you should end up with the same, analogous thing for Camassa Holm. But obviously one has to check the details. But in principle, I think it should work. Because, I mean, the funny thing is, yeah, somehow if you look at the level of KP, then the generalization of Camassa Holm in 2+1 dimensions somehow is the reciprocal transformation of squared eigenfunction symmetry. So yeah, I don't. So okay, it would have to be. I mean, I'm not sure if somebody already did it, but anyway, it could be interesting. I don't know.
Okay, boss. Thank you. I will keep in touch with you. I'll call you.
Yeah, I'll try to send you the references for reduction of Poisson structures to finite dimensions. Yeah.
Thanks a lot.
Okay. Yeah.
So, any other questions from student side? No, I think they are hesitating. Okay.
They're a bit shy today, maybe.
Yeah. Maybe I will ask them to write to you. I mean, if you have.
They can always write to me.
Yeah. They do sometimes.
I should say, Senthil, because Stalin was asking about smooth solutions.
Yeah.
And some time ago, you showed me, I think, for Novikov's equation.
Yes.
With Stalin, you started looking at separable solutions of Novikov's equation, but you didn't. Don't think you went any further with it.
No, we
right?
didn't do anything thereafter because Stalin
Because
and
because one of my PhD students, she graduated 2 years ago, but she actually had maternity leave twice in her PhD, and she even had a third child just after. But she's working in sort of government, some government department doing mathematical modeling now. But anyway, she actually did pursue this problem further, and it's still, we didn't publish it, we didn't write it up, but maybe we can revisit it together. But basically, I mean, if you generalize the separable solution a little bit, you get a one parameter family of reductions, and actually you can reduce them to Palinvet 5 transcendent.
yes.
And this is what she did, the details, and in her thesis. And also she did the same thing for another equation, sometimes called modified Camassa Holm equation. So cubic nonlinearity Picon equations. And that also is related to Palinvet 5, another case of Palinvet 5. But anyway, we could maybe try to revisit it together, because well, I just put a paper on the archive, which it should appear today. It's about the reduction of B family to Palinvet equations. But I checked on the archive now. It says that something's wrong with the PDF. It's saying it doesn't construct. So I need to repost it. But anyway, I can send you the link to that when it appears. I can send you the preprint anyway.
Yeah. Okay.
But anyway, maybe we should discuss again if we can write something about this separable solutions, and because somehow it was your question with Stalin, which eventually made us solve the problem. But yeah, we still never wrote the paper, so good to do it. Yeah.
All right. Okay. Thank you, Andy. So
okay, well, thank you. So yeah, if people want to, I could only say so much in the time, and hopefully it was clear, but obviously there's a lot more details to explain. This is really just an overview.
Yes.
So if you want me to really explain more carefully for the students, then I'm happy to give more lectures, but if we can find a time, yeah, okay.
Yes. Yeah. Okay. Thank you very much, Professor.
Thanks a lot,
Andy.
Thank
you very
and
much.
Happy New Year.
Yeah. Happy New Year to everyone.
Yeah. Happy New Year, everybody.
Yeah. Okay. So I will write to you.
Yeah.
Yeah.
Okay.
Okay.
Bye-bye.
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 Bye-bye, everybody.
Thank you.
Thanks for listening. Okay. Cheers. Have a good day. Bye. Bye.
Bye-bye.